So I've set up a little simulation here to try to explain the principles of using FET, or using a FET to switch something external. And I've set up this little circuit simulation. So starting at the top, we have a 5-volt power supply which is feeding via a multimeter, which is acting as an ammeter. It's feeding the gate of a 2N7000 FET. The thing about using a FET is that the FET is a voltage controlled device as opposed to a current controlled device, which is a BJT, or a bipolar junction transistor. The MOSFET, in this case a 2N7000, is in fact being controlled on and off by its gate voltage, which we can, when I run the simulation in a sec, you'll see how that works. On the other side we have another power supply which is, notice, is at 12 volts, and that is feeding an LED, then through a resistor, through a multimeter, a current multimeter, through to the drain. And it's important to understand this is the drain of Q1. So we have the drain at the top, in this case for the N channel FET or MOSFET, and we have the source at the bottom, which is connected in this case to ground. Now, to control it for an N channel FET, you have to make the gate more positive than the source, which is tied to ground. So as soon as you put plus voltage on here, the 2N7000 will turn on. So in its quiescent state, which let's just open the switch, and we'll let's run the simulation. So if we look at the oscilloscope, and we have an oscilloscope set up here with two channels. So on the A channel, it's looking at the voltage from the switch. In this case, it's the red trace connected to the A channel, which you should be able to see just about here is actually showing ground. It's actually being pulled down to ground by the 1 meg resistor on the gate here to pull it down a bit closer to ground. But essentially it's sitting at ground at the moment, and its current consumption through that 1 meg resistor to ground is actually 49.504 nanoamps. The gate, or the current path through this FET, is virtually nil, so all this current is disappearing down through the 1 meg resistor. This is with the switch open. Notice that the drain current, and that's the current coming down through the LED is currently off. The current through that resistor is 167 picoamps. That's amps to the minus 12. So you can see it's actually smaller than nanoamps. So effectively it's, to all intents and purposes, an open circuit. No current is flowing from the 12 volt power supply through the LED and the resistor to ground, completing the circuit around this circuit here. However, so on the B channel you can see the voltage on the B channel at the moment, which is in green, and you'll see here it's the one at the top here which is showing it's at 12 volts, and the gate is showing at 0 volts. So let's click on the switch and watch the meters. Straight away our meter at the top, which is the drain current, is now showing 17 milliamps, or 17.5 milliamps is flowing down through the LED, and it's showing the LED is now illuminated, and current, 17 milliamps of current, is flowing down through the FET to ground, or effectively the other end of the battery. current flowing into, or if you like, the gate, because it's now energized as it were, is 5 microamps. That's 5 millionths of an amp versus 17 milliamps through the drain. So you can see there's quite a current gain, if you like, here, if you like, a huge change that's driving the LED. So a very small, reasonably small voltage on the gate of the FET will switch a large current, or a much larger current, through the FET, and therefore turning on the LED. It's also possible to feed with suitable resistors a higher voltage on one side or the drain side, as long as you limit the current through the FET. The FET itself has only got a finite current limitation before it explodes. So yeah, that's where it is. So you'll now see on the oscilloscope display that the green line, which is the drain, is nearly down at the ground, all by about 79 millivolts. Sorry, not amps, 79 millivolts, and the A channel is showing that there is 5 volts on the gate of the FET, but very little current flowing through the FET. And if we open that switch again, we'll see it jump there on the oscilloscope to 5 volts, because effectively it's turned off, and the gate voltage is 0. So gate voltage 0, high voltage on the drain, feed 5 volts to the FET, and you saw it switch to ground, and now we've got a high voltage on the gate of the FET. Hope that makes sense.